I'm Paolo Crisafulli. I'm a senior research engineer here at SystemX, and it is my pleasure today to welcome Professor Achim Brucker. Achim is a full professor in computer science at the University of Exeter and a leading expert in secure software engineering, cybersecurity, and formal methods. He is the head of the Cybersecurity group at Exeter, and he leads the software assurance and security research team. Achim has achieved breakthroughs in several domains of particular interest for us at SystemX, based on the use of formal proof, to name a few: formal certification of cyber-physical components, formal verification of the robustness of neural networks, and, as we'll hear today, the formal proof of security protocols. Achim, I'll now let you speak, whether you want to complete this introduction or simply start with your presentation.
Yeah, thank you very much for your nice introduction. It's a pleasure to present our work to SystemX. What I'm presenting today is joint work with Andreas Hess, Sebastian Mödersheim, and Anders Schlichtkohl from Denmark, two different universities in the larger area of Copenhagen. And I'm giving a more of a high-level introduction to the topic of the verification of and validation of security protocols, and also explain what is the particular area that we are focusing on. So let's start with the motivation. What is a security protocol? Those are those protocols and essentially the rule books that our systems use when we, for example, log in into a system. You all most likely have a similar system at SystemX or the University Paris-Saclay, as we have here at the University of Exeter. We have some intranet where we can log in and authenticate ourselves. That entry page is hosted by the university, or at least it lives underneath the university domain. If I click on login, then I'm actually forwarded to a website from Microsoft that looks a little bit different. We can see that the URL is a Microsoft Online one. Can actually also spot that the university changed their logo and not yet at all places. And now this website, the Microsoft website, is asking me for my login and my username, and also a second factor for authentication, and then brings me back to a website that belongs to the university, and suddenly I'm in an authenticated context. So we have two different organizations, the university, Microsoft, that cooperate here, different IT systems, and the communication protocols that make these security features possible. That's what I call a security protocol. They also occur in other places, maybe a little bit more safety critical as well. We have pacemakers that use security protocols for allowing doctors to read out medical data from a pacemaker that is implanted into a patient. And we have seen attacks on those over exploiting vulnerabilities in wireless protocols, essentially allowing an attacker from a 50-meter distance to replace the operating system on that pacemaker. That is definitely something we don't want to happen in real life. So a protocol is essentially a set of rules, conventions, rule book, like when you're doing a board game, how agents or principals exchange messages. We can also understand that as a distributed protocol, and a security or a cryptographic protocol uses cryptographic mechanisms, essentially encryption and hashing, to ensure or to establish security goals like authentication, confidentiality, non-repudiation, and the like. And we not only want to have Alice and Bob, our two standard example agents, to be able to communicate securely without in the free space, without any attacker being in place. Also, if there's an evil person in place, and we usually name that Eve, to also have that start letter E for evil here, that might want to attack them. They still should be able to communicate securely. Let's have a look at an example protocol. That's a very simplified version of it. It's also already rather old. The problem that we want to solve by using this protocol is that Alice and Bob want to be able that they talk to each other and not to somebody else. Consider you're opening the e-banking website of your bank. You want to be sure that you're talking to your bank or that your web browser is talking to the IT system of your bank and not to somebody else's IT system. And similarly, the bank or the bank's IT system would be like to be sure that they are talking to you and not to somebody else. We assume that we have random numbers, unpredictable random numbers available. So attacks on, oh, you can guess a random number is something that for today's talk is out of scope. We also assume, and that might surprise some of you, that cryptography is unbreakable. We assume that Alice and Bob have already public-private key pairs, so that type of cryptography where each agent has a secret part of a key pair and a public part, and the public part is being used for encrypting messages. The secret part is being used for decrypting messages. And we also rule out any attacks on the cryptography itself. So guessing keys, weak cryptographic ciphers, so ciphers where in the meantime attacks have been developed against. That's all we assume. That's not part of our attacker model. And even so, we assume essentially something called we make use of something called the perfect cryptography assumption. There are still problems. So Needham and Schröder in 1978 proposed the following protocol. It only consists out of 3 steps. The first step is Alice is sending a message to Bob saying, hi, I'm Alice. This is the A in the message in the curly brackets. And here's a nonce. A nonce is an artificial word built from a number used once. That's a random number that Alice, when she created this message in this particular protocol run, created randomly, invented. And at that moment, only she knows the value of an A. And as she would like to talk to Bob, she is encrypting that message in such a way that only Bob can decrypt it. Bob receives that message. By reading and decrypting that message, he can learn an A. He generates himself an NB, puts that in a new message, and sends that to Alice, encrypted in such a way that only Alice can decrypt it. And finally, Alice decrypts that message, by that learns NB, and sends that back to Bob as proof that she could decrypt that message. And Needham and Schröder proved or claimed that this protocol established mutual authentication. And actually, that is pretty convincing that it does that, because essentially we can convince ourselves looking at the protocol run. The first step is, hi, here's Alice. I've chosen a random number. Nobody knows it, only me. Bob replies with, hey, I could decrypt the message that you sent to me, as only I have the secret key necessary for decrypting that message. I must be Bob. And by the way, I also have a challenge for you. And the last message then confirms that that Alice can decrypt the message from Bob, proving that she is in possession of the necessary private key. Looks great. Let's look at a slightly different scenario. Let's include Eve. And there's now one thing that might be a little bit non-intuitive. Eve is not an agent that always is evil. As in real life, somebody who decides not playing according to the rules might sometimes play according to the rules and might in certain circumstances be a legitimate, honest participant in the protocol run. And here our scenario starts with the Alice wanting actually to talk to Eve, generating the first protocol message. hey, I'm Alice, here's a nonce that I generated, it's encrypted for Eve, and sending that out on the public internet so that Eve can receive it and everybody else can. And now comes the first step, the first situation in which Eve isn't playing according to the rule book. Eve can decrypt that message, by that learn NA, the random number that Alice has chosen, but instead of replying immediately to Alice, here's your random number and the proof that I could read it, Eve is constructing a new protocol run, generating a message saying, hi, I'm Alice. Eve is lying at that point. Here's the nonce NA. She is reusing the nonce that Alice generated, not according to the plan, the rulebook of this protocol, and encrypting it with the key for Bob. Bob cannot distinguish that this message is not a legitimate one set by Alice. He believes this is a message from Alice, generates the response that the protocol suggests he should generate, saying, here's your nonce NA. I generated also an NB, and he encrypts that for Alice because he believes that this message originated from Alice. This message cannot be cannot be read by Eve because she doesn't possess the necessary secret key for messages that are encrypted for Alice. But essentially, she can wait or forward the message to Alice. And to Alice now, this message looks exactly like the message that she expects in the protocol run that she initiated with Eve, saying, here are two nonces, and then they're encrypted for me, so I can decrypt them. She started the original protocol run with Eve. Therefore, she is now generating a message containing NB, encrypted for Eve, and Eve can, of course, read that. And now Eve has learned the nonce that Bob generated. And of course, she can also complete the protocol run with Bob. And now we are in a situation where we have a couple of security violations. Firstly, the nonce NA and NB are not only known between Alice and Eve, but they are known or shared between Alice, Eve, and Bob. So 3 instead of 2 agents. And even worse, Bob believes that he has now a secure communication channel with Alice, while in fact, he is talking to Eve. And now we can think, or what usually happens is that those nonces or other contents of those messages are then being used for generating a session key for a symmetric encryption scheme. So all future message exchanges are no longer done with the public keys that we used for initiating this protocol, but by symmetric keys generated from the nonces, and Eve could read all those messages encrypted with those session keys. That's not good. And that's the type of attack that we would like to avoid. Here, the problem is that the second message in the protocol looks the same, essentially here on the left and the right protocol run. It doesn't tell us who is the creator of that message, from whom is that message originating from. And we can actually fix that by adding the name of the sender into the second message. And that at least makes the protocol secure against this particular type of attack. Those type of attacks are not only something that happens in theory or on paper. I have here a small mobile app and a smart light bulb. So those light bulbs that you can switch on and off using your mobile phone. And I've set up a small test scenario. On my desk here, I have a couple of Wi-Fi network cards simulating a hotspot for a home network where the light bulb is connected to. And I have a network called Starbucks that simulates an internet cafe where the owner of that light bulb is sitting, and for whatever reason, they want to switch off and on the light bulb at home. Maybe the more realistic scenario is it's not a light bulb, it's a heating system. It's winter, you're sitting in the cafe, you would like to turn on the heating or change the temperature of the heating so that it's nice and warm when you arrive at home. In the internet cafe, we also have an attacker. So now, oops, trying to switch. A little confused. Here's my mouse. Switching on my camera. Switching on my mobile phone. Yeah, it's not, autofocus is working not as good as it should be. But essentially what you can see on the right-hand side of that camera, we now see the light bulb. On the left-hand side, the mobile phone. And I can switch on and off the light bulb by tapping on the mobile phone. I could also change the color whenever I want. And now I'm switching over to a mode where, hoping that everything works. Yep. I have on the right-hand side a program running. That is the disadvantage of Teams. A program running called Wireshark that captures the network traffic. This is what the attacker would be running on a public Wi-Fi, for example, and it just records all the network packages. And we can see that there is some HTTP traffic going on. I will just quickly stop the recording and restart it so that we continue without saving, that we have a fresh screen. And if I now start switching the light bulb on and off, we can see that there are packages being sent. And yeah, we see it's HTTP, it's unencrypted. And now I'm doing a reset again on the capturing so that I have one dedicated action here. Continue without saving. The light bulb is currently off, so I switch it on. And I'm capturing now. I'm stopping the capturing here and save that into a file. Save as, and that was switching it on. Now I'm switching, swapping screens here, show you my terminal. So this on pcap and G file, that's the saved network traffic. It's saved in a standardized format that those network capturing tools use. I've written a small Python script that converts that data into essentially a command for the command line tool curl that contains the JSON data that encodes, so we can see that here, essentially that encodes the command for switch on that light bulb, plus, yeah, which server to connect to the current token being used in that session and the like. And I now can just copy and paste that into the command line. And while that happens, because that command should switch on the light bulb, I'm switching it off. Syntax highlighting in the terminal is slow, so that takes a moment. So we now have a situation, the owner switched off the light bulb, the attacker recorded a piece of network traffic, and is now trying to replay that. And in a secure system, that wouldn't work. But we will hopefully see, it's really slow today. I don't know, but we are nearly there. That if I now hit enter, oops, malformed input. But it did switch it on, right? Don't know why I'm getting the error message, but the on switch works. So we can see that the attacker can replay that message. And here the problem is not necessarily that the data traffic wasn't encrypted. that would be one way of fixing that, or at least making it harder for the attacker. The other problem is that the system doesn't check the freshness of that message. So essentially, if they would have added a nonce, so that the light bulb or the system that operates the light bulb could check, I've seen that package already, that's a duplicate, I ignore it, that attack would not be possible as well. So it is a real problem. Oh no, let me switch that off again. So just because a system uses encryption, they are not necessarily secure. There's a lot of other aspects that we need to look at, and essentially we are focusing on that, how to compose, how to combine security features like cryptography and ensure that the system that we build is secure. That's also not a new problem, so to speak. It took actually 18 years to find that flaw. And we hope that by automating that work, and already in the early 2000s, late 90s, a lot of work in that area started, coming up with the verification idea, applying verification to this problem, saying, hey, we have a system specification. We would like to have a formal proof that our system is secure. If we talk about verifying a system or the security of the system, we need to talk about against the type of attacker. There is nothing like the perfectly secure system. We always have to think about it is secure against a certain type of attacker. And in this work stream of symbolic protocol verification, we use an attacker called the Dolev-Yahoo attacker model, named after the two people that presented that model first, Danny Dolev and Andrew Yahoo. And we can ignore essentially the mathematics here. The idea is we assume that we have perfect cryptography, both public key and or symmetric key as well as asymmetric encryption. They work perfectly. Agents can generate perfect random numbers. But we have an attacker that controls the network, essentially. So the attacker can intercept messages, read messages, and create and send new messages. And of course, if they know the private keys necessary to read some encrypted message, they can learn new content and use that for composing new messages. We can then formalize this, and I'm not going through all those rules that we see here, but just to give you an idea, in the middle of the screen, we have, for example, the rule that says, if an attacker could read a message M that has been encrypted by a symmetric encryption scheme using the key K, and the attacker also knows the key K, then they also know the actual content of that message. Again, in practical terms, that just means if I know an encrypted message and I also know the key required for decrypting that message, I know the unencrypted message text. I can just decrypt it. We have a similar rule for asymmetric encryption. We have a rule for if we look at signatures, so a message is being signed to ensure its authenticity. That message always looks a little bit surprising to a lot of people because we know the signed message and we immediately know the message content. But again, signing or recall, signing ensures authenticity. Also in real life, if you sign a contract, put your wet ink signature underneath a contract, that means you're happy with the terms and conditions of that contract. But everybody who obtains that signed contract can read the content of the contract. So that one is not confidential. If you want to have it confidential, you'll need to encrypt it in addition. We can already see we might have a lot of different agents being involved. We can construct arbitrarily complex messages. If you're a little bit into formal analysis, you can see that might become complicated. And earlier work, or a lot of not only early work, one also has to say very successful work, thought about, let's focus on a practical tool that helps us to find problems. And if needed, we limit the complexity of messages, we limit the number of agents, we limit the number of parallel protocol runs or sessions, if that helps us to quickly find issues. And there are a lot of those automated tools where you just specify a protocol run, you run the tool, and you might get an attack. And I can also show you one of those tools that has been developed by Sebastian, one of my collaborators. On the left-hand side, you can see the specification of the Needham-Schroeder protocol that I've shown on the slides earlier. The tool supports an input language which is more or less close to what I also used on the slides. The core part is the action specification in line 10 to 13, where we exactly see the three messages being exchanged from Alice to Bob, Bob to Alice, and again, the last message, Alice to Bob. We have a little bit of prelude and type declarations. Think a little bit like in a programming language where you need to declare your variables. We also need to declare the initial state of the system. So we need, for example, to tell the system, our analysis tool, that Alice in the initial system state knows that there is Bob. She also knows her own private key that's in from pkna, and she knows a function pk that essentially models a key server for looking up public keys. So this so-called Alice and Bob specification language is not that hard to learn. Not saying it's totally easy, but it's not very hard. And my undergrad students are able to specify protocols using that language. And there's a tool called OpenC. And if I run that on this specification, then essentially in no time, so it took me 5 minutes or so to explain the attack on the Needham-Schroeder protocol on slides, and I'm not sure if it was good enough that most of you actually have understood it. It's a very subtle issue. OpenC returns an attack trace in less than 30 milliseconds. So really no time on a laptop where my audio equipment and video equipment is running in parallel as well. And this attack trace, it's a little bit hard to decipher, but essentially the I over here is Eve, our attacker, and the X502 and the X25 are Alice and Bob. And this textual notation essentially is an attack trace that is exactly the attack that I've explained on my slide. So really, really useful, really, really helpful. And we can also quickly check. So if you remember, the fix for that issue was adding the name of Bob into that second message. I'm saving that. Rerunning OpenC, and now the behavior is different. Now OpenC tells me I verified that for one session. Now I'm running it for 2 sessions, and we can already see it takes quite longer. I mean, it's not hard to guess that hopefully in a couple of seconds, there will be a third line saying I verified the security of the protocol, or that the protocol established mutable authentication, also for 3 sessions, but it takes longer and longer. And at some point we might say, now we are getting, 3 sessions is good enough for us. I don't wait any longer. Hit Control-C, say that's fine enough. But that's now only a statement about the absence of an attack within the attacker model, the Dolev-Yao attacker model that OpenC uses for 3 sessions. There still could potentially be an attack that is for 10 sessions or for 11. We just don't know. Those tools, as I said, very successfully used. A similar tool developed by previous colleagues of mine when I was working for SAP. They analyzed SAML implementation. So SAML is one of those protocols that allows single sign-on across different authentication providers, and found a problem in the implementation of Google in 2008. And Google not only fixed the SAML implementation they had in place at that point in time, they also acknowledged the use of those tools for finding that problem. So really useful and helpful tools. So looks like we have solved that problem. In a certain way we have very good tools for finding attacks, but those tools are usually not developed and optimized for proving or showing that there is no such attack. Essentially, the no such attack statement comes from, yeah, we analyzed it, the tool did run for quite a while, didn't find anything. And it's much better than if it immediately finds an attack. From an implementation perspective, the encoding of the rules, what is the attacker allowed to do, what rules has the protocol, how does the inference internally, the reasoning, the algorithmic reasoning works internally, that's usually done in an axiomatic way. It's just written down, and whoever is implementing those tools might have made a mistake, overlooked something, and that might result in a bug in those tools. And the implementations are usually not that easy to understand because they're heavily optimized for speed to be able to analyze large instances, large protocol instances, and to be very fast. As seen, this NSPK protocol attack has been found in no time. On the other hand, we have another type of formal method tools, usually associated with something called interactive theorem provers. And one example is COC, that you in France know very well. I'm using Isabelle for my work. They follow a slightly different philosophy, or actually a very different philosophy. Their architectural design has been done in such a way that there's a small trusted kernel, often only a few hundred lines of code, that somebody needs to trust and audit, and that is a generic kernel. Everything else, all trust that we need to put into systems based on Isabelle or COC, rely on, there's this one kernel that does the difficult, critical work, and if you want to ensure or convince ourselves that Isabelle works correctly, we mainly need to audit a relatively small piece of implementation, and we only need to do it once, regardless in which area we apply a tool like Isabelle or COC. As long as we don't then just inject axioms in whatever we do on top of that, and that is called usually a conservative development or conservative embedding. The idea essentially is, instead of just stating axioms, we are deriving them, we are proving them, so that we ensure the consistency with respect to the base logic that the theorem prover provides to us. And furthermore, the Needham-Schroeder protocol that I explained is, of course, very simple in the sense that we looked, or the scenario that we looked at is very simple in the sense that we looked at this one protocol in isolation. Even if OFMC is analyzing multiple runs, multiple sessions of that protocol, it only runs multiple sessions of NSPK in parallel. But it doesn't, for example, analyze what happens if I run NSPK and SSL in parallel. And there could be other problems. And also a lot of modern systems, modern protocols rely on a shared database, for example, for noting down revoked cryptographic keys that are no longer trustworthy, that are updated, and the updates need to be available to all agents. And that was essentially the motivation for our work, can we use a theory improver, and can we also support composition of different protocols, have a composable security analysis, and support shared databases. Now, using a theory improver for protocol analysis is not that new. Larry Paulson has already done that also already, I think, in the 90s. Modeling protocols in Isabelle essentially each rule of the protocol being modeled with together with the attacker rules. We can see something here where we have the first message of the NSPK protocol saying, yeah, if the agent A has a non-used term, if nonce is not used yet, then they can extend the current state with that first message, put that into a set of traces, and then the agent B can respond to that. The problem with that approach was that essentially you needed to model each protocol individually, including infrastructure like attack rules, which made it a rather manual approach. But given the particular approach of conservative embeddings, also very trustworthy, which is a positive aspect here. And we wanted to have a higher degree of automation. We don't want to specify each protocol completely from the beginning, including all the attacker model, as well as wanting to have a more user-friendly specification language, not necessarily relying on the fact that people can use higher order logic, the logic that Isabelle uses for specifying those protocols. Also, Paulson's model uses a rather abstract model of messages and types, similar to what OpenC does. But yeah, in reality, protocol messages are much more complex. They have certain message formats, and we wanted to come up with a message format that is more realistic, that is closer to real-world implementations. Composition, I already said, shared state, I already said, and of course, automation should be better. So why all that? Let's have a quick look, very abstract look at a modern single sign-on protocol, essentially something like SAML. We have channels in that protocol that run over TLS. TLS is the basic encryption protocol that the internet uses. So that's essentially your S in HTTPS. We have that authentication question that NSPK essentially solves. And if we model that formally, we end up with a long specification. So if we start doing that in a more concrete way, not only the pure single sign-on. So this is the pure single sign-on, so essentially the NSPK part. But then we need to integrate TLS and all the negotiations that TLS does. And that becomes very lengthy. That's only the first part of it that goes on. And it's definitely, at least I think we can all agree on that, it's too complicated. And again, if we then combine two other protocols, we need to do the composition, the integration, again, manually ourselves. So that's why I want to have a composable approach, where we specify our single sign-on, we specify TLS. If we specify TLS as a standalone protocol, the overall specification might be a third to half, maybe a third to 2/3 of a slide, but not going over multiple slides with all those details. And would also not need to decrease the font size, so that would be much nicer. So why don't we do that and call it a day? The problem is that if we analyze TLS in isolation and SAML in isolation, it's not obvious that the composition running those two protocols together is secure. And just to give you an idea on what the problem is, I have two very simple protocols here on the left and on the right-hand side. On the left-hand side, it's a simple protocol only sending a signed message to B. And in the right-hand protocol side, it's a two-message protocol. B starts the communication with sending a nonce to A, and then A also sends a signed message, including the nonce, to B. And if we look very closely at those two messages that A is sending to B, they are both signed messages, signed with the private key by Alice and nothing else. So essentially here, there is a shared key being sent to Bob, whereas here it's only the nonce. A nonce is a random piece of text. A crypted message, if the cryptography is perfect, is essentially also only a random piece of text. So if Bob is receiving this message here, he cannot easily distinguish if this is a message from protocol, this protocol on the right-hand side or the protocol on the left-hand side. And if he gets confused, or if an attacker is able to make Bob, for example, to believe that the message that he receives is from protocol A, he might use the nonce as a shared key, or the other way around, use that encrypted message as a nonce and derive something from that, but giving the attacker the ability to influence what happens next in a certain way, and that can lead to attacks. So we need to have additional checks that show that, for example, the structure of the messages doesn't allow for these type of confusions. And that is something that we were looking at in Isabelle. What type of conditions do we need to check? And finally, we're able to come up with a system where you verify two protocols and then have relatively simple additional checks that then give you the answer that you can easily combine them or not in a secure way. For stateful composition, so as I already mentioned, a lot of modern protocols have a long-term state. Think about revoked keys or the like, and we wanted to model that as well. That then also, revoked keys essentially adds another very important security feature to the mix, namely the declassification of secrets. That is also something that in an ideal world hardly ever happens. In reality, happens very often. Something is a secret, something is confidential up to a certain point in time, and then suddenly it is no longer. For example, we see that in the business world, if you do collaborate with a company, if you maybe merge and acquisitions, acquire another company, up to the point when you inform the stock market that you plan to acquire that company, that's a very big secret. And after you published it, it's no longer a secret. And we need to be able, or we wanted to be able to model those kind of situations as well. And that is essentially what we also achieved. So a first important result that we have is for a whole model of security, of a protocol security model. So essentially, how do the messages look like? How can they be composed? Andreas proved in Isabelle that the security analysis on a typed model, which annotates every piece of the model with what it is. This is a public key. This is a private key, essentially. This is an agent name, is as good as doing that on an untyped model. And the analysis on a typed model is much easier because a lot of those confusion attacks cannot happen. And what we then need to ensure, of course, is that the type information also in the untyped model is implicitly at least visible in the term structure. We then extended that model to support protocol composition. And we also could show that if you have two protocols that you've proven already to be secure, then essentially you only need to check that the set of labels and the message structure satisfy certain conditions, and then you can also compose them. And the resulting composed protocol is secure as well. That is usually easier than directly composing the protocol, first writing a specification for the combined protocol and then trying to analyze that. And finally, we did work on the automation. One difficult part here in the correctness proof or security proof of those protocols is they generate this trace set of messages that's an infinite set that essentially is inductively defined. We all, or people that work with model checkers and theorem provers, know that induction is the part where automation usually doesn't work that well. We were able to come up with an idea where we can use an automated algorithm for computing an abstract over approximation of that message set and use that in a clever way in the proof as a witness for the absence of attacks within Isabelle, but always implemented in such a way that if our approach would be buggy, if we would do a mistake in the implementation, it would never result in successfully verifying a protocol that is not secure. It would always error towards the direction that we are suddenly not able to prove the correctness of a protocol that actually is secure. So our maxim, our design strategy always was to ensure that if our tool says it is secure, then we have a very high security guarantee with respect to that Yahoo attacker model, extended with concepts like shared databases, shared state, and the protocol composition aspects. And tools in Isabelle look very much different to OFMC. I can also give you just a very quick idea how that looks like. So what you see now is Isabelle. The Isabelle interface looks a little bit like a modern IDE. Maybe these days, the tool that many people know and that works mostly similar on a certain similar way are Jupyter notebooks. So the idea is you have an editing window here in the middle of the screen. And you have an output window here, so it's not embedded like in Jupyter notebooks, but essentially whatever is seen here on the screen is in real time being processed. And if I'm at the end of that command block, which is rather long because that's TLS, I get some output here. So I did load that already before I started my talk because, frankly speaking, it takes a couple of minutes to parse that lengthy specification. And it not only parses that specification, it analyzes it and does already a large number of fully automated proofs for basic properties, deriving the requirements for composability, and a couple of other proofs that are later useful for doing actual security proofs. And instead of encoding the protocol rules directly in higher order logic, which would look even more frightening to many people to what we see here, we have a trace-based specification language that we included. That was not a good idea. That we included into Isabelle, so now we see that the processing takes some time. That is not yet as user-friendly or friendly for beginners as the A and B specification, but is closer to what people that specify those type of protocols use than directly using the logic that Isabelle is using. And on the long term, we hope that that we are able to make that even more user-friendly, starting with syntax highlighting and maybe adding another level of abstraction on top of it. And then essentially split up here, what is the unique feature? I'm only aware of one or two other systems that allow that. We have on the one hand, Isabelle commands that do a fully automated verification of the protocol, but we can always, so to speak, intercept the automated proofs and seamlessly switch over to an interactive or manual analysis. So for example, if we are in a situation where our automated proofs are not clever enough, a well-trained verification engineer could step in and support Isabelle in doing that proof, maybe proving some invariants, proving some helper lemmas that are useful, injecting them at the right position into the automated proofs, and stay within the same framework and doing essentially a co-verification where the automated system and a human are doing the verification together. This system has also been used successfully in a case study. Sebastian Mödersheim in Copenhagen did do an analysis of essentially a contactless payment system for public transport. So essentially something similar as the public transport card that you have in the Paris area. Also looking at the protocols and communication aspects there, and actually did found a problem in those protocols, and the company updated their implementation and fixed the issues being found, which is very nice for and a very nice success story indeed for a system that is relatively young, only a few years old. And yeah, key takeaways. If you're not interested in protocol verification and maybe not a security expert, the key message that I would like you to get from this talk is there is no perfect security. Security is always only justifiable or explainable with respect to a threat or attacker model. And if you compose components that are secure, and that's not only true for security protocols, that's true for all aspects of security, the composition of secure building parts doesn't necessarily yield a secure system. There is still an additional security analysis required. For the formal methods experts, the key takeaway is we can formalize large aspects of security protocols in Isabelle, and we can have actually both a high degree of automation and the high assurance that Isabelle gives. And the one system that shares the vision of switching between automated and security proofs, and that is also very successfully used in the wide area of security protocol analysis, is Tamarine, which is developed at ETH Zurich. That's all from my side. With that, I'm open for questions.
Thank you very much. So yes, questions are welcome from now on, and I have a few. So maybe we can wait for others if some questions are. I haven't seen any in the chat, but I'm checking.
Anis, I'm seeing him.
Yes,
I hope I have pronounced the name correctly. Oh.
Yes, maybe I can start.
Yes.
So I would have two questions. The first one is related to the conclusion that we will have once we used Isabelle, we formalize the model, and we execute actually the proving process. So what is the conclusion? So we can have two cases. The first case is I have a proof that my protocol is secured. with regarding to the adversary model that we are considering, and also the properties that we are going to prove. But what happens if we don't have a proof?
We don't have a proof. So what you don't get at the moment, and that's a limitation, is you don't get automatically a counterexample generated. At least not in a nice and friendly way. That is another interesting line of research. Isabelle has a counterexample generator built in. And maybe that could be adapted to generate more understandable counterexamples also for such domain-specific applications. But at the moment, frankly speaking, you don't have a proof, and hopefully your interactive exploration gives you some insights where the problem is. But you don't get a message sequence chart, for example, like OFMC can generate with a detailed, an attacker does this step and this step and this step, and then the system ends up in a state that violates a security property.
Okay, thank you. Can I go with the second question?
Yes, please.
Yeah. So my second one is more related to the composability in general. So you spoke about how we can check the properties once we compose two protocols, and this actually makes me think about, okay, I compose actually two protocols, and I end up having an attack. I mean, a counterexample or an attack showing how we can actually break down the security of the protocols. So I'm wondering if we can use that, or we can use Isabelle to try to find a modification of the protocols in which we don't have a state with the same attack.
If you have already both protocols analyzed, then the compositionality check is much more syntactic, and highlighting there where the problem is definitely much easier. We can also improve on that on the tooling side. Yes, it might be possible to come up with fix suggestions. Also, very interesting line of work. Haven't started that yet, but would be something I would be keen looking into if resources allow. I'm not aware of any work that does this already. We have those type of repair approaches for programs and program verification. And I would assume that similar ideas can be applied to this domain as well.
Okay. Thank you, and thank you again for the presentation. It was really very, very, very instructive and very clear. Thanks again.
So maybe I can go for my very basic questions, which are actually just a way to check that I've gotten the main points of your presentation. So basically, so you have designed an Isabelle theory, a set of Isabelle theories to model protocols and their composition. Is that right? Is that the main focus of the work? And Tamarine, sorry?
Yeah, please continue.
Yes, okay. And Tamarine is the name, right? Is the name of the...
No, Tamarine is the competing product, so to speak.
Okay,
so the different, so what we did is, yes, we did model all the protocol aspects, and that looks like what most people would consider to be the standard use of Isabelle, where you have your data type definitions followed by lemma and type definitions and the like. That is one aspect. And then we have the automation approach, where we did more system development in terms of coming up with new proof methods. So implemented new proof methods, new top-level Isabelle commands for executing proofs, for doing compositionality analyses, as well as for parsing and encoding this trace-based protocol language into something that Isabelle understands. So, and that is maybe more what people not necessarily associate with Isabelle development, but Isabelle can also be being used as a framework for developing formal method tools, and we are making use of that. Our tool is called PSPSP, which is a little bit, a joke, partly for a long name. And yeah, I wanted to mention here Tamarine because it's the only other tool that I'm aware of that allows you to switch nicely between interactive proofs and fully automated proofs. But Tamarine isn't built on a generic verification system. They are now encoding just all the rules directly as axioms in the system, and are lacking on the argument of trustworthiness that we want to make by being a conservative embedding or conservative extension of Isabelle.
Okay. So the automation part makes it suitable to some extent for non-experts. Experts in the security, experts in the security domain, but not necessarily in the proof in the theorem prover field, right?
Yes, exactly. That's what
you wanted to
that's
achieve.
the underlying other mission I have in my life, demonstrating that generic theory improving tools can be made suitable or can be used for domain-specific developments that are then suitable for domain experts, but not necessarily verification experts.
And so this is all published in AFP, so we can download it and try it for whenever. Okay.
Yes, and updates are also published to the AFP and then become visible in the main RFP whenever Isabelle has been released, because the AFP release cycles follow the Isabelle release cycles.
Okay. And if we want maybe a more complete bibliography around this topic, or maybe you gave, I saw there were a few references in your slides.
I'm happy to share the slides with you, then you have those references. It's essentially a paper in ACM. What is it? Transactional security and privacy. And we are currently, so there's a conference paper in CSF on the automation aspects. We are currently working on a journal version of that one that should also be submitted very soon. But before submitting that, I would like to implement some performance improvements first. I'm currently working on those.
So yes, also this is currently still ongoing work, right?
Yeah, it's still work that we are improving on.
Okay. I think. Well, maybe one last question, if no one else has. I'm curious about the very beginning of your presentation. I don't understand how Eve can decrypt Alice's message.
Oops.
The flow.
Don't be afraid. Yes. Don't be afraid of that. It is very subtle. The important part happens here. So again, we don't know that Eve is not a nice person. So Alice wants to talk to Eve, sends this first message. So this message here is indeed encrypted for Alice.
Oh, okay.
For Eve, sorry. And by that, Eve learns the norms that Alice generated.
Okay.
And then Eve reuses that norms, and number used once, that's a violation of the rules, to generate a message that claims she is Alice, and she sends that to Bob, encrypted for Bob. What's not? Okay, No. So here, this is the part where she sends a message saying, I'm Alice,
Okay.
but it is encrypted for Bob. So essentially, here's a contradiction in there. We usually would expect the, oh no, not here. Here it's not visible. Where is it? So here, essentially, here's then in the response message, Bob generates a message copying over that nonce, generating a new one, NB, and here encrypting it for Alice, because he believes that the message came from Alice. And this is the message that Eve cannot read directly. But it looks syntactically exactly like the message that Alice is expecting anyway. So based on that first, and that also is the other reason why this first message is important. Because Alice has sent that first message, she is waiting for a message that is encrypted for her and contains two nonces. The one that she generated that she can validate, and a new one. So that looks totally fine for Alice here in step 4. And then in step 5, because she initiated the protocol with Eve, she is encrypting that message with Eve.
Okay.
Eve's key.
That's why if you add and Bob, she will know that there is a problem.
Yeah. So it is subtle, and also it took 18 years before somebody discovered this problem. Yeah, it's not that experts look at that, and it also wasn't the case that within those 18 years, nobody looked at that protocol. A lot of people looked at that protocol also with more formal techniques and missed that. So it's really not, it is really a very subtle thing, and we as humans are not very good in analyzing distributed systems. That might be the other learning from that.
Okay, thank you. All right. Well, if there are no more questions, I think we can all thank you very much.
Yeah, also thank you very much for the invitation.